Okay.
Third time's the charm. All right. So today we're going to be talking about homeostasis, negative and positive feedback loops. We're also going to talk about the reflex control pathway, cell membrane transportations, and then we're also going to be talking about osmosis and tonicity. So let's just get on homeostasis. It's pretty easy. Homeostasis is our body trying to seek equilibrium. A few ways of that is we got temperature, we got heart rate, blood pressure, we got glucose levels in the blood and insulin. But we're just going to talk about temperature. It's pretty easy, pretty simple. So we want to stay, let's just say this is 99, this is 96. This is our set point, right? That's the thing we want to stay at. So we're going to have, within our body, they find that temperatures fluctuate. So we're fluctuating, sometimes we're down here, over here, right? It's like, whoa, we're going back and forth to this set point. That's where we want to be. Set point is, that's the place. That's the prime spot. So we have negative feedback and positive feedback. Negative feedback is going towards this set point. So this is what we're seeing. Negative feedback, we're going past, and then we're going up. How does the body do that? It's called the reflex control pathway. So basically, we have a stimulus. I'm going to move over, which goes to the receptor, which pushes towards the control center to the effector, okay? This is our, let's see here, this is our efferent pathway, and then this is our afferent pathway. Okay, so we're going to explain this in terms of this. Okay, we got stimulus. That's going to be the temperature, right? It's getting cold. Our receptor, right? Our skin feels it. Our neurons, they're firing, which tells our hypothalamus. The hypothalamus is like, hey, look, we gotta warm up. So let's shiver, right? Shivering creates warmth. So that's what we're going to do. So that's the effector, right? We're shivering. Oh, if I can spell. So we're shivering. If it's hot, we're gonna sweat, all right? We've got different ways that bring us back to the receptor. These are different pathways, and that's the reflex control pathway. That's what it is. Okay, I think that is all we need to talk about homeostasis. We got our set point. This is time, by the way, if you wanted to know. That should be it. Okay. Trying to make this as simple as can be. Okay, so let's get to diffusion, like channels, right? Getting stuff into our membranes of our cell. So we got diffusion through channels. This is, we're going from, I'm going to keep this up here because we're going to use it twice, high concentration to low concentration for all of these. We're not using any energy. This is just concentration gradients. So we're going high to low. So an example of this mechanical, right? We're going to draw a little cell, little mechanical, right? We're going to have a high amount of these little particles and a low amount over here. As this will respond to pressure, temperature, and a stimulus, I think. So these are going to bump off here enough so that this is going to open up. And these little bad boys, right, this is different now, sorry, going through the concentration gradient. So those are pretty they're pretty awesome things. So we're going from high to low. It's selective. Saturation is possible. When we talk about saturation, it means there's only so much that can fit through here at a time, okay? So when we have saturation, we'll just make a linear graph, right? You can't, it's not really gonna be like, whoop, you can't have that. It's gonna be linear, because when we're saturated, we can only fit so many people through a doorway, right? You can't fit 5,000 people through a doorway. You can fit 5, right, at a time. That's it. Okay, so that's saturation. No energy needed. Oh, I need that. So, let's get to carrier mediated. Oh my. Transportation, diffusion. Okay, so carrier mediated, we got carrier proteins, right? These are our carrier proteins right here. I'm just gonna draw them stupidly. Okay, basically, this little dude, he's gonna go in there. These carrier proteins are gonna open up. On the other side, they're gonna change shape, so this little dude can go. We're going from high to low again. Pretty simple. Of course, we can get saturated. It's pretty competitive. I think, what is that called? Oh yes, so glucose does this. Glut, G-L-U-T. And you can look it up later. I'm not going to explain it. So that is our concentrated gradients. Okay, so now we've got active transport. So active transport. We got 2 types. We got primary and secondary. So primary, we got secondary. So primary uses ATP, secondary uses indirectly uses ATP, okay? So basically we got a sodium potassium pump. Basically we have this. We have 3 Na pluses to 2 K pluses, right? And we use an ATP, those go through. That's primary. Primary can get saturated. Most of these can. You can only fit 3 and 2 through there. You can't keep on pushing more. But it's highly selective. It's like this can only do this, okay? Indirect, so secondary, we're going to do indirectly. We got an symport, an antiport. Symport, basically, we're going to have our cell here, right? I'm just going to draw it really simply. So we have a high concentration of these circles, low concentration over here. We have our little thing. It only lets these go through, and then we're having this. We're going to have a high concentration of these in here and a low out here. Okay, right? So with secondary, one goes against the gradient, one goes to the gradient. So we'll just say this: against the gradient, one goes against and one goes with. So this is symport, this goes in, this also goes in. Okay, this one's going against, this one's going with the gradient. So antiport, we're still doing one goes with, one goes against, but now we'll say this one, oh, this one's hard to explain. One goes against, one goes with. And they have to, basically, instead of going together, one goes out, one goes in, okay? So let's just say there's like one of those, right? So now this one's going, wait, no, that was totally right. No, that was right, I'm sorry. So this is going against the grid, or this is going with the gradient. Wow, I did do that wrong. This is going against the gradient. This is going, or with the gradient, against the gradient, okay? Antichord. Okay, that is it. Basically, that one's highly competitive. Of course, it can get saturated. The directions there, these ones both go in. This one goes out. This one goes in. Yeah, but that's it. They indirectly uses ATP. Okay. I think the last thing is, I think it's osmosis. Okay. So we got two things we're going to talk about: osmosis and then tonicity. Okay. So osmosis is comparing concentrations. So you can have something that's osmotically, we're going to introduce some new terms. So we got iso, hypo, and hyper. So this is more, same, and this is less. Okay, so this applies to both of you. You can have something hypoosmotic, hypotonic. So that's how that works. That's the roots we're going to be using. So osmosis is, simplest terms, it's water wanting to be, well, we're talking about concentrations, but water wanting to be at equilibrium. It wants the concentrations to be the same. So when we're talking about osmotic, we're talking about concentration. So here's an example. We're going to have water or something, whatever this solution is, and then we're going to have a cell. Okay? There's our cell. So we're going to use osmolarity. And osmolarity and molarity are similar but different. They had to make up a new form of units for osmosis, so they use osmolarity, okay, which is osmoles over liters. Molarity is moles per liter. Okay, those are different. Don't mix them up. Osmoles is basically, it's just talking about concentrations, what it is. Okay, so we're going to have, usually a cell has 300. We're going to say this is 300, right? This is isoosmotic. It's the same. Okay, so if, say, this is now 400, all right, we got 400, 300, and we'll just do 200 just because we can. Okay, this solution is hyperosmotic, right? It has more, concentrations more. 300 iso, 200 hypo. So that's how that works. Tonicity is different. Tonicity is talking about how this affects the cell. So you can have something that's osmotic, that's like isoosmotic, like these concentrations are the same, but they're different. But your tonicity is going to be different. Okay, so your tonicity is, instead of having them separated, we just took that cell and we put it in that water, right? My box wasn't big enough, right? So now if we're 300 here, we're 300 here, we're isotonic. If, say, we're just going to be talking to the cell because it confuses a lot of people. Confuses me sometimes. Say this is 300. Say this solution is going to be 400, and it's not permeable. Permeable is super important with this, because if it's permeable, it's going to even out, right? It's going to go into this cell. So that affects things, right? Because it wants to be, it's going to go into the cell no matter what, if it's different. So say this is not water is going to go out of the cell. So the cell is hypotonic, is less. It's going to shrivel up, okay? We're going to lose water till this is the same as this. Hyper, right? This is going to be 200 right here. We'll say this is 200 instead of 400. Now water is going to rush into the cell. We're going to rush into the cell. It expands, and at some point, say you have a cell with, an example is dextrose. Dextrose is a glucose, and it's metabolized immediately. So we're going to metabolize it, and we're going to have 0 things out here. This cell is going to burst. It's so hypertonic, right? But you can have things that are osmotic and isoosmotic. So say we're just going to use this. We got 150 NaCl, right? And then we're just going to do 150 dextrose. I think it's like 5%. I think this is 0.09 or 0.9%. I don't remember exactly. But that's 300. That's iso, right? That's the same. That's the same. We're going to get rid of this. It's iso. That's 300. That's 300. But when we come to tonicity, we're going to have this dextrose is permeable. NaCl is not permeable. This dextrose is going to go into the cell, get metabolized immediately. So now our little bucket here, right? It's at 150. This is getting metabolized immediately. It's going into cells. This is still 300. So now this is, it's going to be hypo. It's going to be hypotonic, right? It's because it's now, it's trying, or I meant hyper, my bad, hyper. Water is going to rush into here because it needs it, right? It's trying to be equilibrium. I think that's everything I got. Thanks for watching. Hope it's an A.